Hi, I'm Jennifer Krug, and today we're at Deep Run High School. This is my college prep chemistry class, and we are on Unit 2, Matter and Energy. And today we're going to be looking at some phase diagrams and some heat curves, and we're going to do a lab with dry ice. So first, I wanted to talk to everybody about the phase diagrams. So I will pass these out real quick. There you go. And can you pass them over there to them? Pass them down. 4, 2, 3, 4, 2, 3, 4, 2, 3, 4. All right. So I have some examples of heat curves and phase diagrams on the board. And this first one over here is what we call a heat curve, okay? This is a heat curve, all right? And what's happening in this curve is as you start to input heat, eventually you're gonna notice something. You're gonna notice that the heat is still going in, but the temperature stops changing, okay? So these areas here and here, where the temperature stops changing, those are your phase changes. So the sloped areas are your states of matter. So on your worksheets, okay, at the top, if you go to your heat curve, I want you to label it and say solid, okay? Then go to the next slope and say liquid. And then go to the top slope and say gas, right? Now, there's actually 2 phase changes that happen at each constant temperature zone. It depends on the direction of energy flow. So if you're putting energy into the matter, right, where we're going from a solid to a liquid, where energy is being added, what do we call it? Who knows? It's very easy. What do you call it? What? Melting, right? Right? And if you're going the other way, right, where you're taking energy out, this is freezing. Pretty simple. And up here, putting energy in, the common word is boiling, but the science word is vaporization. And what's interesting, if you look it up online, a lot of times you're going to see evaporization with the E in front. Evaporization is specific to water. Vaporization with the V in front is just kind of a general term for all liquids, okay? When we're going back the other way, condensation, okay? So we can tell a lot from this graph. And when you come over here to the side where it touches, right, where this temperature is no longer changing and it's being held at a constant temperature, if you come all the way over here, whatever this is, this degrees, we call this the melting point, right? Because it's only one temperature. It's a point on that graph. Same thing up here. When you come over here, we call this the boiling point. Now this is pretty good, this heat curve, but it doesn't show you all the possible phases. So that's when we come over to the phase diagram. So both of these are phase diagrams. Okay, and I have a phase diagram for the carbon dioxide, which is the dry ice that we're going to look at in a minute, and I have a phase diagram for water. Hey, Sam. Thank you. You can kind of sit up front if you want. You'll notice that they're somewhat similar, a little different. This one, this curves a little back, this or a little forward, and then this one curves a little back. So other than that, they're pretty much the same. So you have to think of it in terms of pressure pushing in, right, and temperature heating things up. So when you're looking at the phase diagrams, I want you to think of, don't worry about the numbers at the bottom so much, think of it in terms of if you're really low temperature, right, you're going to be cold. And if you're a really high temperature, you're going to be hot, okay? And then over here for pressure, if you've got a really low pressure, that means it's not pushing very much. And if you don't have anything pushing on you, right, then you can expand out. So you're kind of spreading out if you don't have a whole lot of pressure pushing in. So down here we're talking about matter spreading out. And when you have high pressure, everything's pushing in. It's kind of pushing in on the matter. So it's pushing together. Right? So then it kind of makes sense which states of matter you're going to be in these locations. So if I'm over here in this top general area and I'm really, really cold and all my matter's being pushed together, which state of matter do you think I'm going to be in? Solid, right? And obviously if I'm over here and I'm really, really hot and I'm spreading everything out, then you're going to be a gas. And that means liquid goes in the middle. Right? Now, just like we had our changes over here where we could see that the temperature was constant, you can't really see that temperature's constant over here, but you can see each point along this line, you can see that the temperature is changing based on the pressure. So what that means is the freezing point and the melting point doesn't just depend on temperature, it actually also depends on the pressure. Okay, so obviously this way would be melting, this way is freezing, going back and forth. You have vaporization, started to write boiling, vaporization, condensation, all right. And then notice on this curve, we now have new section that we didn't have over here. On this curve, we have this lower part down here where it can actually go from a solid to a gas. 1 atmosphere is where we are right now. We're at James River. We're very close to the river, very close to sea level. So we're at 1 atmospheric pressure. And at 1 atmospheric pressure, the carbon dioxide is actually going to skip the liquid phase. It's going to go into the gas phase. And we call that sublimation. Sublimation, okay? And if it goes back the other direction, it's called deposition because it's kind of depositing the ice. It's like when it freezes outside, you get a frost and the water vapor turns into ice crystals on the ground. Notice we have 2 little dots on this curve. We have right here and we have up here. These are kind of important dots. This one in the middle, notice the solid, liquid, and gas all come together. That is called the triple point. And that's where all 3 phases are in equilibrium, okay? You're doing all of these phase changes literally at the same time. Up here, it's called your critical point, okay? So the critical point is where you can no longer tell the difference between the liquid and the gas because liquid and gas is at equilibrium. So if we look at these, because literally all these little labels would be the same over there, what's different? Why does dry ice sublime but water doesn't? Why does dry ice go from solid to a gas but water goes from solid to a liquid? Kind of depends on where you are on the curve. So if we're at 1 atmosphere, right, and you come here, notice that I hit this part of the curve where you go from solid to a gas. But when you do the same curve for water, 1 atmosphere is up higher. So if you come across, right, you go from a solid to a liquid. So when you're looking at these phase diagrams, you have to pay attention to where the 1 atmosphere is. Because wherever the 1 atmosphere is located, that's going to tell you, hey, right there, that point, right, if I come across, I find my 1 atmosphere and I hit this point and I drop down, then that is my melting point. Okay? And if I keep going over here, right, where it goes from a liquid to a gas, and I drop down, this is my boiling point. All right? So you can get the liquid, you can get the melting point and the boiling point from the phase diagrams, but it's dependent on the pressure that you're looking at. So for normal conditions, we say 1 atmospheric pressure, you come across and you drop down. But if you're higher or lower, obviously the melting point and the boiling point are going to change depending on where you are. talking about dry ice. The dry ice, okay, is negative 78.5 degrees Celsius. That's really, really cold, okay? Basically in Fahrenheit, that would be negative 109.3 degrees Fahrenheit. So normal ice, right, is about 0 degrees Fahrenheit. So this is 100 degrees colder than normal ice. In order to work with it, we have to wear special gloves. So I have some cold insulating gloves. Get it out of the bag. And you can see right away, it's already starting to sublime, right? This is why it's called dry ice, because it skips the liquid phase and it instantly turns in to the gas phase. So right now, we're looking at the solid, and the solid particles are they're under a lot of pressure, right? And they're all close together. But as it switches into the vapors, you're seeing the molecules kind of fade away, right? Are they actually fading away? Where are they going? Are they disappearing? What do you guys think? They're spreading out, right? They're getting so far apart, you can only see them when it's really close together. But once they get far apart, the individual molecules are so tiny you can't see them anymore. So we're going to be looking at their physical and chemical properties today. And what I'm going to do is I'm going to have each pair of you guys come up, and I'm going to give you a mason jar, and I'm going to break off a little piece of the ice. I'm just going to show you this real quick. Break off a little piece of the ice, right? And we're going to fill it up with water, with some warm water. Okay, so when you come up, what I'm going to have you do is I'm going to have you get on some gloves. These are not cold insulating gloves. These are just gloves that are slip proof to keep you from dropping the glass. And we're going to drop in the dry ice, okay? And you'll instantly see it start to boil, okay? When you come up, one partner is going to carry this, right? One hand under, one hand over, and then the other partner can pick out a color of food coloring, all right? When you get back to your areas, I want you to drop in the food coloring and see what happens. Does it change the color of the solid at the bottom? Does it change the color of the gas coming out the top? Or does it only change the color of the water? And then we'll talk about what we just saw, okay? So go ahead, put on your goggles, and then call up the rows. Maybe the first row can come up, and I'll start breaking off some little pieces for you. Remember to put on your gloves. One partner put on the gloves, the other partner can pick out the color. Cut it. Yeah, you can just take one. I'm having to make it a little smaller because they didn't restock the dry ice. This is a small piece of dry ice.
Don't mess up.
Wait, are we allowed to put the diet?
Yes. Yeah. Okay, the next row.
Come on.
Come on up.
AJ, move your head.
Caroline, you put so much in.
I don't recommend it. I think it'd be fine.
What did you guys see in terms of the food coloring? It only changed the water, right? We're going to learn this a little bit more details later this year, but when you look at a molecule of carbon dioxide, the molecule of carbon dioxide is kind of stretched out like this, and it's very symmetrical, okay? And the fact that it's symmetrical is the reason that it's not attracting the food dye. The food dye is a polar molecule, and when you look at water, water looks more like this, and you can see with the water, the electrons, these little dots represent the electrons, and they're more on one side than the other. that means it's more negative over here than it is on that side, whereas the carbon dioxide's evenly distributed. And it's just like when you play with magnets, okay? On my board right now, I have these little magnets. Everybody's used to playing with magnets, right? If you try to put the same ends together, they don't want to work, right? But if you put opposite ends, then they attract each other. And so that's kind of what's happening. Your food dye is a molecule that's sort of polar like a magnet, and your water's polar like a magnet, and so they attract each other. But the carbon dioxide doesn't have that polarity, and that's why the food dye won't go and attract to the dry ice. You're gonna take your finger, okay, kind of get your finger wet in the soapy water, and then you're gonna rub it around the surface of your mason jar on the rim. And then you can take out the soapy string and just very carefully slide it across the edge of your jar, and you'll get a giant bubble. Whoops, that one popped a little too fast. I think mine's a little too charged.
Looks like a mushroom cloud. It's called
Guys, when you're done making your bubbles, you can add some of your soapy water to your mason jars to see what happens. Yeah. So it's turning the bubbles colors. Thank you for joining our class today here at Deep Run High School. I hope you learned a little bit about phase diagrams and heat transfer of matter and energy.